Okay, hello everyone. It's my great pleasure today to welcome Matteo Broggi from the Leibniz Universität Hannover at the Institute of Risk and Reliability to our online seminar on interval methods and control engineering. And Matteo, before joining the group in 2016 in Hannover, he graduated in nuclear engineering at the Politecnico di Milano in 2005. Afterwards, he joined the Institute of Engineering Mechanics of the University of Innsbruck in Austria. And there he also received his PhD degree in civil engineering in 2011. And after that, he joined the Virtual Engineering Center of the University in Liverpool as a postdoctoral researcher. And yes, I think mostly during that time, during that time, he started with doing lots of research on numerical and computational tools for risk analysis, reliability and uncertainty quantification, model updating. And I think that's also one of the issues that Matteo will talk about today during his talk, distribution-free Bayesian updating with hybrid uncertainties. Matteo, we're looking forward to your talk.
Thank you very much for the introduction, Andreas. And thank you very much, everybody, that you are here now to attend to this presentation. So I want first of all to activate the virtual pointer. Let me see if I can. Laser pointer. So can you see it on the slides?
Yes.
Okay, that's perfect. Okay, actually, just because I realized that I didn't know that the pointer was getting duplicated. So I'm in this position, I prefer it. So, okay, again, thank you for being here, and thank you for your kind introduction. And in this talk, I want to concentrate. First of all, I want to acknowledge that this talk is mainly based on work that I've done together. Student from the institute, Masaru Kitara, that has finished his PhD and left the institute like 2 months ago. So that is the main acknowledgement to do. And so why I want to do this talk? This talk is because, as you know, and since you are all attending this sequence of seminar, you know about the spectrum of uncertainties, and you know that practically we, as engineers, we like to analyze 2 types of uncertainties that affect our models. The first type of uncertainties is the unavoidable, the physical uncertainty, unavoidable uncertainty, but also aleatory uncertainty, that are what is usually what we consider as random, affecting our structures and systems. And the second type of uncertainties is the modeling uncertainties, that is the lack of knowledge, or I can say it uncertainty. This is due to the fact that our model are not precisely known, our parameters affecting the model are not precisely known, and so on. But this spectrum uncertainty is not a hard division, but is actually a mixture of the two, right? We have always physical uncertainty and modeling uncertainty mixed in together. The problem is that we use 2 different types of mathematical approaches when we have to deal with these 2 types of uncertainties. For aleatory uncertainties, we use the word coming from the mathematics of probabilistics and statistics. That means we use to model them random fields, random variables, stochastic process, and so on. While the epistemic uncertainties are used and modeled with other methods like interval, p-boxes, and the propagation is done using optimization type approaches. So we like to categorize things. So what we usually say, we say that the category 1 parameters are constant and known. Category 2 parameters are pure epistemic. That means that they're constant, which value is unknown, and we usually use interval variable or fuzzy variables to represent them. The third category is the purely random and known, that means crisp distribution, and we use the pure probabilistic approach. And finally, we have category 4 parameters that are affected both by randomness and undetermination. That means that we have like a mixture of two random variables that are with unknown parameters, for example, and this is p boxes or interval fuzzy variables. This is the kind of world where we're working with, and we want to do, we have models, and we want to then update the parameters of the models. What I mean is that when we have this kind of epistemic uncertainty, this can be reduced by means of observation and experiments. But this is done through, in this talk, is done through Bayesian updating. So Bayesian updating is a particular type of stochastic model updating. What we want to do with stochastic model updating? Stochastic model updating, practically, we have two types of uncertainties that are acting at the same time on our model. The first type, of course, is aleatory uncertainty that make the output model stochastic. And this is because we, for example, hypothesize that the scatter that is shown in the experiment is purely caused by aleatory effect. Of course, there can also be epistemicity affected by our data. That means that there is a precision of the measured data on the measurement experiments, but we assume that this imprecision in the measurement is negligible compared to the scatter shown by the experiment. That means that the scatter is purely aleatory. And the epistemic uncertainty is affecting only the model. And this epistemic uncertainty that is affecting the model is the cause of the discrepancy between the model output and the observation. So the question is, how do we increase the fidelity of the model? The fidelity of the model is then going to be increased by reducing the epistemic uncertainty as much as possible based on the knowledge gained from the observation. Now, that means that the epistemic uncertainty will then a kind of model of physical quantities like uncertain input, approximate model, or even information. And the fact is that we have real data. The experiments of the physical process are not direct measurement in this approach that we are doing with Bayesian updating. The real data is not a direct measurement of the model parameters. We assume that these are impossible to be detected directly because of too expensive experiment or destructive experiment and so on. So we only have an indirect measurement of the uncertain parameter. What we are then doing is then compare the experiments and the model outputs. And the final question is, how do we do to increase, how can we increase the fidelity of the model, and how we can include the knowledge gained from the experiment into the inputs? And for this, we use Bayesian model updating. Bayesian model updating is based on Bayes' theorem. That means that we put together three ingredients that are the prior distribution, the likelihood function, and the evidence to obtain posterior distribution. The prior distribution is expressing our initial knowledge about the range or about the distribution or about some knowledge of the unknown epistemic parameters that are playing into the model. These, for example, are modeled by uniform distribution. And then here it's saying something, for example, interval. But what I mean is that in Bayesian model updating, we use the language of probability to treat epistemic uncertainty. In my opinion, this is the only case where this is indeed allowed to do. If you're doing analysis with epistemic uncertainty, you only have intervals, you don't use sampling methods, but you use optimization methods to propagate the interval. In the case of Bayesian model updating, it's allowable, it's correct to associate a distribution when you have epistemic uncertainty. So if you only have bounds, that is interval from the epistemic uncertainty, you associate uniform distribution, but you can put other shapes that are in the prior that depends on how confident and how much importance you want to give to certain value of the parameters with given your a priori knowledge. So you can use, as I say, if you don't have any idea at all, you put a uniform distribution. If you are more or less certain of some value, some more important value, you put a Gaussian shape, you put a triangular shape, or if you have like preference on some interval, you can put trapezoidal shape, and so on. The likelihood function, I will just say practically it's very briefly because there will be a longer discussion about the likelihood function. It's just the way how we incorporate the information delivered by the experimental data and how to we update the prior PDF and the distribution of the parameters. And finally, the posterior distribution, it's the combination of the prior knowledge and the data in order to have then an updated knowledge of the epistemic parameter. Problem is that it's this formula is very nice, it's very simple, but as usual when we're dealing with distribution, we have unknown normalization. And the normalization means that we cannot generally, in the most general case, we cannot actually have a closed form solution, but only but we can only get knowledge of the posterior by means of sampling methods. The problem is samples to be generated, it's complex because the shapes of the distribution can be very complex, especially in high-dimensional input space. Input parameter space, and then what we usually use, we use method based on Markov chain, but directly using Markov chain in the is starting from the prior distribution in it's in a, let's say, not intelligent way. It works only if we have something like a flat and widespread PDF, because then it will be possible to then propagate the samples with Markov chain and capture the actual PDF. But the problem is this is not really a realistic posterior, because what we want to do is to reduce the it's to reduce the uncertainty of the parameter as much as possible. So what is actually a more probable posterior distribution for the input parameter is going to be actually a very peak concentrated over a very, very small range of parameter. And that means that, for example, if we have a very nice posterior, it is going to be like this, and we start from an uninformative prior as shown here, it will be very, very difficult for a Markov chain to actually capture this area. And we can actually even have multimodal concentrate PDFs, and then it means that our Markov chain will reach only one area and not get all of them. That means that we need to much more advanced algorithm. And just to give you an idea of which algorithms are available, I will not go into details. The most widely used algorithm that can solve this problem that I listed before is transitional Markov chain Monte Carlo. This is done by adaptively constructing intermediate posterior and propagate the samples in intermediate step. The problem is that starting from very wide uninformative prior, you need a lot of steps to reach the posterior and a lot of corresponding model calls. That means that this becomes extremely inefficient when the model you are calling is expensive. Because of this, another method, this method has been enriched recently by adding adaptive Kriging-based metamodel to the TMCNC procedure, so that only when you need you evaluate the full model only when you need to improve the accuracy of the metamodel, and you define when you are to do this by means of learning functions. On the other hand, another method has been recently developed, that is the Bayesian updating using structural reliability method that reformulates the updating problem into a reliability problem, and then use subset simulation to propagate the samples in this reliability problem. And again, this is another reformulation of the updating problem that it still requires a lot of steps, but less steps than traditional Markov chain Monte Carlo, and does already less samples, and also can be then we can then use the adaptive metamodel method for reliability analysis to improve the numerical efficiency. And here you can see some of the papers that have been done in this direction. But a big problem that still I didn't discuss is the problem of the likelihood, right? So I put it on pause in the previous slide, because the problem of the likelihood with hybrid uncertainties, it's still where the key efficiency and key accuracy of the Bayesian model updating is all concentrated. The likelihood is actually how we improve and now we introduce the knowledge of the given from the experiments into the model parameter. So let's assume that we have a case where we have only epistemic uncertainties. That means that all the model output is purely deterministic, and the parameters affecting our uncertainties are the type 2, so only purely epistemic. No aleatoricity in there, in the model. So how do we interpret it and how do we describe the likelihood? Because the likelihood is still need to incorporate the information delivered by the experimental data, right? So if the model is deterministic, how can we create a likelihood that capture the epistemicity, the aleatoricity that is shown by the experimental data? Remember, as we said at the beginning, experimental data is purely affected by aleatoricity. So the model has nothing that is, the model is output is purely deterministic. How we do that? Well, we have to assume and to make assumption on the reason and on the shape of the discrepancy between the model output and the experiments. And these assumptions are due to, for example, model error or measurement error, right? The measurement error is much easier to address than the model error, because the model error are going to be practically due of an actual choice of the epistemic nature of our model, or the approximation done by the model. While the measurement error that can be treated by means of probability distribution. Okay, so if the discrepancy between the test data and the analysis is assumed to be normally distributed, that means that it's purely like a sum of noise and so on, then the idea is to use the likelihood function that is a Gaussian distribution. And why that? Because the Gaussian distribution gives, of course, the largest amount of uncertainty according to the maximum entropy principle. And the Gaussian distribution in this case will look something like, for the likelihood, will look something like this. The probability of our data given the model parameter and the model class is going to tend to be a product over the likelihood of every single available data point, experimental data point. And we have to compare the output of the model, that is a function of the model parameter, and the value of the experiment. The value of the experiment is then considered to be as the random part, and the in our Gaussian distribution, and the output of the model is going to be then the mean of our Gaussian distribution used for the likelihood. The data then, of course, can be multidimensional and can be then, because you can have more than one, of course, the observation at the same time, and you have then, you produce the likelihoods. In the case where there is a correlation between the values, and this correlation represents the correlation between the values observed dimension in the data in the experiments, If we decide that there is no correlation between the data and so on, we just do the sum. We can just do the sum of the difference between the output of the model and the experiment, sum all of them, and then put them in the exponential to do the quotient. One problem is we have this parameter that is the variance of the likelihood, and this is something that we don't know, we might not know, or we have to assume. So what usually happens is that the variance of the output will be included in the set of model parameter that needs to be updated, and they will be updated by Bayesian updating at the same time. Now the question is it Gaussian error a good assumption? Well, it's a good assumption if indeed the model is accurate but not precise. And the only cause of difference between model output and experiment is just kind of noise, right? But the likelihood can also be other shape and other discrepancy model for other model. What it means then to have a good likelihood. So let's assume the good model that captured by the likelihood, by having a high value of the likelihood, Well, if this is the set of experiments you have, let's assume that it's just one observation we are taking, so one-dimensional model output and one-dimensional experiments. If this is our set of experiments, a good model, it would be something like this. So, for example, a model that when we associate our likelihood, that is the Gaussian that we introduced before, when we then evaluate the value of the likelihood of each experiment and then product over them, this will lead to have a big value of the likelihood. And this means that it's a good model, a good representation of the experiment given from the model. On the other hand, a bad model would be something like this, for which many likely will be very, very, very small values. And then when I do the product, of course, this likelihood overall is going to be very bad. And this is a model that represents the experiment poorly. But now, what happens when we have hybrid uncertainties? That means that we have a mixture of epistemic and aleatory uncertainties, and that means that the output of the model is not anymore a single point, but it's going to be a probabilistic distribution. Why that? Remember, we are doing a sampling procedure behind. That means that we set the values of, we generate with the algorithm the possible value of the theta parameters, right? That means that when we fix theta, the output of the model is going to be purely stochastic. Having the model output purely stochastic, we can then evaluate the likelihood directly by actually evaluating what is the value of the probability density function of the model output that are purely stochastics, and inserting the value of our experimental data in there and evaluate the PDF of the experimental data. And then, of course, doing the product of all for each experiment to get the overall likelihood. The problem is that we need to, of course, have a very accurate knowledge of the output PDF. And this is most probably a non-closed form solution and will require then a double loop approach. That means we will have an external loop going over the value of the theta parameters, or the model parameters, driven by the Bayesian model updating, and then we will evaluate the distribution of the output of the model by means of Monte Carlo simulation, for example. And we need to, for example, to describe this PDF with kernel density from Monte Carlo simulation, and this will lead, remember, this loop on the theta is already, I don't know, 20, 30 iteration because of we are using something like a conditional approach Monte Carlo, and then we have to very accurately represent the PDF with Monte Carlo. That is practically computationally impossible. We can make it faster by using, instead of the Marco-Chain Monte Carlo, using a adaptive kriging procedure. So we'll code the model less, but it's still, we need, when we code the model, we need to have the full accurate PDF. But let's look again what it means to have a good model in this case. Well, by changing the value of the epistemic parameter, the output distribution of the model will completely change. For example, for a certain value of the parameter, I will get this set of randomly generated output value from the model from Monte Carlo. I will fit then a kernel distribution and then evaluate directly this axis point that are the experiment and evaluate and get the value of the likelihood. A poor model, another model can be like this, will be a better actually likelihood, because it's then covering all the data and associating a good value of likelihood also for the people, these samples that were outside of the first distribution we found. And a bad model would be something, for example, like this. And you can see like good, better, and bad likelihood function, right? But as I said, this is going to be very expensive. So what we use actually not the method. We don't generate the whole. We decide that it's better not to generate the full PDF and the full likelihood practically from the model, but we want to use something more efficient. And this is done by using approximate Bayesian computation. That means that we approximate the likelihood by using, instead of using the full PDF, we use some distances, some distance metrics that evaluate the distance of the stochastic output of the model from the available experiments, right? Usually in PBC, they use something like the distance can be the mean, the distance in the mean, the distance in the variance, how much difference is in the quantiles and so on. But what we found that is very accurate is to actually use stochastic distance metrics, because we can capture different properties and different level of uncertainties represented by experiments and stochastic output of the model. For example, if we want to consider only the distance between the center of mass distribution, we use Euclidean distance, and then we can use something like Maranowitz distance. Or if you want to actually capture completely how different are the distribution, we use a measure of the distribution overlap, for example, like the Bhattacharya distance. And Bhattacharya distance is what we found that it works very well. And this is defined as the minus the logarithm of the integral of the square root of the product of the distribution of the data distribution out of the simulation model. And it can be actually done descriptively by using binning algorithm and by comparing then the probability loss function does the histograms of the data from the histogram of the simulation. One problem we have is that with this is not really the Bhattacharya distance is not a triangle, doesn't satisfy the triangular property. So the problem is that when there is an overlap, the distance is infinite, and this is not going to work in our Bayesian approach. So what we usually do is then a two-step approach. First, we update so that on the Euclidean distance of the center of mass, so that we ensure that the center of mass distribution is the same, and then we do Bhattacharya distance updating. The next step I want to discuss now is about how do we deal then with distribution free model updating. What we need with distribution free model updating is that when we have no knowledge on the inputs, we making an association, making an input that are both epistemic and aleatory, making an hypothesis of what is the distribution function affecting my aleatory is actually a big hypothesis, right? If we say my input are Gaussian, or my input are beta distributed or gamma distributed, this is already a big assumption that limits practically the search space of all the possible, the search and the input space of what are the possible aleatory inputs. So we then wanted to do something that is to be free of the assumption of the family of the distribution function of our aleatory input, the aleatory input space. And the question is, how do we calibrate the PDF of this aleatory input when the families are unknown? And how do we incorporate this observation also when we have actually dynamic data available from our model and from our experiment? So what we used the concept of staircase random variables. Staircase random variables are univariate random variables that are only defined by the bounded support and the first four moments. That means we fix then practically we don't say what is the distribution family, and we only describe the distribution by the mean we want to have, the variance we want to have, the skewness we want to have, and the kurtosis we want to have associated to our random variable. And we do that by associating then a staircase density function. This is a piecewise constant. That means practically it's practically an histogram, a normalized histogram, where we define our we divide the input, the bounded support in a certain number of bins, and we associated a certain height to each bin. Okay, and this is done. For example, I will explain how in the next slide how it's done. For example, if we have support -1, 1, and this set of parameter for mean, variance, skewness, and kurtosis, this is the resulting shape for 25 bins, 100 bins, 200 bins. So we have to do, the more means we use, the more smooth this staircase distribution becomes. Now, how we determine the value of this Li? This is done by using an optimization problem on the moment matching, and with constraints given to the moment. Why constraints? Because not all the possible value of the moments are actually allowed. There are some mathematically hard constraints that have to be assigned when we start then exploring the input space of the possible 4 moments, and for each of this set we will then solve this problem that will give us the value of the Li, and this is the constraint we'll put when we do this search of the possible, when we do also an updating procedure over these 4 moments. What are these constraints? The constraints are, for example, that the mean must be between the lower and the upper bound. Then these are considered optimization. So that the mean must be between lower and upper bound. Then the variance must be positive and smaller than this quantity v that is connected to the bounds. And other constraints are also given on the third and fourth moment. So let's have a look of what are the results of this optimization argument that gives us the staircase. I forgot to say, this optimization problem is actually a convex problem, so it's very, very fast to solve for each set value we put to the values of the parameters. Let's have a look, for example, if we put support of 0, 2 and moments of 1, 0, 33, 0, and 1.8, this corresponds to a uniform distribution. And this looks like a uniform distribution to you, obviously, but this is actually the results of the optimization algorithm from the staircase distribution. So this is actually a staircase distribution fitting over this set of parameters, and as you can see, is actually correctly fitting a uniform distribution. For example, if you put instead of this set of parameters, this is a beta distribution that is left skewed, and this is the corresponding staircase distribution. You see there is a problem. This should go, of course, down to 0, but the optimization algorithm cannot identify exactly that it goes to 0, but it's still pretty precise for the scope of the analysis. And finally, you can see the flexibility, because if we put, for example, this set of parameters, well, we end up actually capturing a shape that is bimodal. And this bimodal distribution, it's absolutely not part of any family of distribution that we are available to define on the traditionally available to define on the 0-2 interval. And we can then model very, very complex stochasticity shown by the input affecting the model. So yes, we are able to approximate a very, very wide range of density and shapes, and also very highly skewed multimodal distribution. We can capture them. That means that we can characterize the aleatory inputs with unknown families with no limitation. And of course, what we want to do is then a model updating over these distribution-free families. And what we do, we will set, when we do then model updating with no knowledge at all of what is the family of the distribution associated to the aleatory input, what we will do, we will then associate uninformative prior intervals on the mean that has to be between the lower and upper bound, on the variance, on the skewness, and on the fourth moment. And then we will do model updating given the available information and get information, extract information from the available data. So is this working? Well, we've done a small test, for example. Let's say that we have completely uninformative data, a completely uninformative prior that is just saying we don't know is the family, we don't know anything at all, and we just know that the support of our experiment is between -5 and 5. Then we generate our data, our observation from a normal that is between 0 and 1, and we run model updating, and this is the posterior we get, okay? And you can see that we get a very accurate and precise posterior regarding the first moment, second moment, and we have some more difficulties to update the third and fourth moment. And this is an open problem that we still have to solve, but more research is going on in this to improve the updating, let's say, for the third and for the higher moments. And what is the kind of the posterior when we generate an sample from this posterior distribution? Well, we get something that looks like this. So you see that actually we were more or less, I mean, we didn't have much data. I don't remember exactly how many data points we had, but we managed to reduce from this prior distribution that we were practically getting anything was, any distribution was possible between the -5, 5 space. We end up with reducing a lot the uncertainty. I think that my okay, it was I'm sorry, my PowerPoint is crashing. I don't, it's not, yeah, my PowerPoint crashed. I'm very sorry, just 1 second. Yeah, PowerPoint crashed, sorry. Let me restart. Great. Can you see the slides again?
Yes, they're here again.
Okay, let me just go then to the right slide where we were before. Okay, sorry about that. Let's go ahead. So now I want to discuss about some, how much time I still have, sorry?
As much you need.
Okay, okay. So that is the end of the, let's say, theory part. And I now move on to some numerical example and some analysis that we have done with this Bayesian updating procedure. I have 3 examples here. In the abstract, I only talk about 2, but actually I decided to add the third one. Because the first one, it's this Bayesian updating procedure when we only have a model that is purely deterministic. So I want to show you how indeed the Bayesian updating works accurately in this case, and you'll actually compare this with another updating procedure. Then we will have the updating of a simple example, but a dynamic model that has a 2 degree of freedom shear building. And the third problem is the NASA Challenge 2020. Sorry. So the first example is the LR mode. What is the LR mode? The LR mode is a small structure for which we have experimental data available, and this model is a replica of this benchmark structure and represents a simplified dynamical equivalent of a airframe. This model was this data was provided by the LR, and this model was practically disassembled and reassembled 130 times. And excited with a random signal in the frequency 0 to 400 Hertz to extract the first 30 modes of vibration of this structure. And here I show you, this is available experiments, and this shows the scatter that was given in model mass, model damping, and model frequency. This, what I mean with scatter is, here it's 100% the nominal value, and this is practically how much percentage of variation was shown by the experiment, and this is the equivalent model of damping and model mass that is scattered shown by the experiment. Now we're using our data for the updating only the frequencies. We had also a numerical model available that was Nastran, and this was the these are the first 4 modes of vibration that was captured by the model, and they were corresponding, of course, to the modes that were measured by the experiments. And which kind of uncertainty was affecting this model? Well, the uncertain input, they were all affected only by epistemicity, pure epistemic, and they were representing stuff like the stiffness of the joints, stiffness of the cord that was supporting the model during the vibration test, mass of sensor cables, of screws and glues, and so on. And so on, because the model was always the same, but as I said, was getting disassembled and reassembled. So of course, for this stiffness and sensor mass and so on, it was accurately calibrated to be precise this, let's say, nominal value, but it was not completely under control. And there was, of course, variation in how this was, how these parameters were every time it was reassembled. As I said, we used then Bayesian updating, and what we did, we actually compared the Bayesian updating to another procedure called interval field updating. Now, in a finite element, it was pretty fast, but since we were using traditional Markovitch Monte Carlo with a lot of steps, what we used practically use the neural network. For the interval updating, we used an optimization argument that was global optimization plus neural networks, while for the neural chain, we use neural chain and neural network. Why we use neural network and not some more advanced method? Well, because we use the same network for interval field and Bayesian updating to have the same, let's say, the same playing field. We have done then two analyses. Why two analyses? Because we want to see what happens when we have limited available experimental data. So the first analysis was done with the full experimental data set. That was 86 experiments, and then in the second analysis, we used a reduced experimental data set. That was only 5 experiments. Well, this is just showing the meta model accuracy, and this was actually the worst performing meta model. It was the one capturing the 7th frequency, and it was very, very good, as you can see. The output. So in red, we have the scatter shown by the measurements. In blue is the output of the interval model updating, and in green of the Bayesian model updating. And what we captured, that we saw that in interval was really struggling and missing completely some of the outputs, frequencies, while Bayesian model updating was getting very, very good and accurate results. This I can show. This shows the posterior distribution of the input parameters. Of course, for the interval, it's just giving you bounds, while for the Bayesian model updating was giving you full distribution. And this is actually showing the color corresponds practically to the value where the distribution was getting higher value. But you can see actually that in this case, we were getting something like bimodal distribution for some of the inputs. We can practically infer that while doing this experiment, some condition at some point changed. And that's why the distributed posterior was actually bimodal, because it was actually to something that was not apparent, obvious from only looking at the data. We could see it from the posterior by characterizing this bimodal behavior. When we use instead the reduced set, the thing actually changed, because what happens is that with Bayesian updating, we have too much scatter. Why is that? Because we have too much scatter, because when we have limited data, the prior is too much important practically. We need more. The more data we have, the less important becomes the effect of the prior. So in this case, we were starting to get to go towards the correct posterior, but it was too wide. So practically, it was not able to. With few data, we were not able to actually get an informative posterior. While the interval updating could get some information out of the few data more efficiently, because the interval was always collapsing over the data available. The second example we're going to talk is now we start to look at what happens when we do hybrid uncertainties and distribution free. So the model is a modification of the engineering application introducing the first paper of Bayesian updating by Beck and Au. in that Bayesian updating, they had deterministic output. Of course, this we changed it. We changed by having practically by having epistemic inputs associated to it. That means an aleatory input. That means originally it was only epistemic input. In our version, we had a mixture of epistemic and aleatory input. So in now and back, we only had log normal with two most probable values that are 1.3 and 0.8, and to observe the frequencies. In our example, to make it more, sorry, I didn't want to press next. We have aleatory and epistemic uncertainty. The aleatory input is still the two stiffness X1, X2, but they are modeled by not knowing anything about the distribution and having uncertainty on the characterized by staircase random variable. And in this case, the data we observed was 100 pairs obtained by assign a posterior PDF defined in our back. We did a two-step approach because in the first step, we practically generate the area of the possible posterior distribution where we need to propagate and capture the posterior in the sense of having the same center of mass. That is the two-step approach that I said before, right? First, we push the samples to the center of mass of the experiment and the center of mass of the data from the model are well overlapping, and then we do, and this is of course the result in the first step. So you can see in the first step, we actually move the output of the model, it is here in blue, towards the center of mass of the two regional space, and then I identify this regional space to which I will do the optimization with the Bayesian updating with the Bhattacharyya distance, with the likelihood using the Bhattacharyya distance. And these are the I skip the step of the Euclidean and just show at the end what the result of the Bhattacharyya distance. So in red, with the dashed red is the target value. The solid red is actually the most probable value out of the updating. And for the 4 moments, the first moment, second moment, third moment of the updating, which is the Bhattacharyya distance. And you see that this is for the first cloud of points here, and this is for the second cloud of points here. And the corresponding, these are the two inputs, and the corresponding output frequency are here, where you see in black are the observed experimental data. In blue is the output of the updated model, and in red it was actually the space of the output we were getting from the prior assumption, right? So you can see that we reduced a lot the uncertainty, and not only that, we actually captured very accurately the scatter shown by the experiments. So what we can, it's crashed again. PowerPoint crashed again. I'm so sorry. I don't know. Oh, no, it came back. It came back. Okay, so the proposed updating framework practically allowed us to combine the Bhattacharyya distance and the staircase function, capturing the calibration of both the aleatory epistemic uncertainty without any assumption of the distribution family. So, of course, we knew that the distribution was supposed to be log normal, and we knew the correct value, but we started from no assumption at all, and we actually captured the real. We managed to capture the this distribution. I think I will skip this where we started putting in some dependency between the data, because I think it's less interesting. We managed to capture dependencies, but it was, I don't think it's very interesting. I want to skip to the another challenge problem, because I think it's much more interesting. So it is another challenge problem. The another challenge 2019. It was defined in the following way. So practically, we had a available set of dynamics observations on 3 different outputs, And we had the model. We had the model, we had the observation, and we didn't know anything about the model parameters. So the model parameters, we knew that we had 5 aleatory inputs, of which we didn't know anything about what kind of distribution they were, what kind of family they were. We only knew about the fact that they were bounded. And then we have 5 epistemic input and 4 epistemic input. This is a mistake, it's 4, not 5, and 9 design parameters. There were then 5 tasks. We had task on model calibration and uncertainty reduction on the first set of operation. Then we had the reliability analysis, propagating this model into a performance function and computing the reliability by the bounds of the reliability. The reliability-based design optimization, design tuning, and model updating on the second set of observation. As I said, the 5 aleatory inputs, they were completely unknown family distribution, and only the support of the distribution was given. The support was normalized so that nobody would have, and we didn't know anything about the model. The model was completely obfuscated and black box. We didn't know anything at all, and on the model parameters, so that nobody would get like an insight of knowing some physics behind the problem, to really test the algorithm as much as possible. Epistemic were only given only a support, again also normalized on value 0, 2, and we were given a set of 100 observations. So in our solution, we decided to do the updating of the epistemic and aleatory parameter at the same time with Bayesian updating, by associating to each distribution of the aleatory input a staircase density function. That means that we ended up increasing the epistemic parameter space, because we had then 4 epistemic parameters associated to mean, variance, skewness, and kurtosis for each random variable. That means that we had 20 epistemic parameter that we introduced for the 5 aleatory inputs that were then kind of pivots, and then the 4 epistemic inputs. So let's look at the results we got actually from the updating. Now this is what we had as output from the model from the prior. Okay, so here was the data that we have available. You can see that this was the observation D1, observation D2. And here is the output from the from this completely informative prior. You can see that we have a big mess for this, and it's absolutely not showing what is available as an observation. And same also here. And here even we have something interesting, because we have like a diverging, unstable output. And this red bar represents the requirements of the reliability that we had. And the requirement of reliability was practically the output model should have been always inside these red bars. We did then our updating procedure, and this is the posterior distribution for the these are for the mean and variance, skewness, and kurtosis for the 4 random variable, and for the 5 random variables, and for the 4 epistemic parameters. And you can see that for some of them we managed to. This is the prior range. So the prior range was 0, 2, 0, 1, and so on. And you can see that for some parameters, we were able to really reduce the uncertainty very, very, very well. For others, sadly, we couldn't extract much information. Probably our assumption is that because these parameters, our hypothesis is that because the parameters were actually not very sensitive towards the output. What we did then, we tried to then propagate these posterior distributions that we got by like associating extracting interval out of each parameter by making a cut at 0.5, and we then propagated this into pbox, and the corresponding model. This is a comparison between what we had from our model after the updating and the observation, and you see that we actually managed to reduce a lot the uncertainty and get very nice agreement between the model output and the observation. When we started, we used the second set of data, the one and the set of data D2 that you see before. the updating was even actually better, much better, working even better. And you can see that we actually managed to completely remove that instability behavior and completely remove and then always not completely, and completely remove also the non-reliable behavior we are not exceeding these reliability bounds that we had before. So I hope to conclude, we saw how we managed to practically capture very high and flexible model updating with no assumption in place by using both this staircase distribution, stochastic matrix with Bayesian model updating, with the pre-hypothesis model updating and the Bhattacharya distance, and managed to get very, very interesting and good results in very complex and challenging application. And just to conclude, here are some references that on the analysis that has been done in this is presented in this talk.
Okay, then many thanks, Matteo, for a very interesting presentation. And yes, now I would like to hand over the microphone to the audience. Is there anyone who has some questions? In fact, I have at least two questions.
Okay.
I think your two key ingredients in the presentation have been the steps of the definition and the usage of the metric that you defined. And the second key ingredient has been more or less a moment matching approach that you had when you designed your staircase distributions.
Exactly.
And when we have a look at the metric, how, let's say, sensitive are your results with respect to the actual choice of the metric?
Yes, we tried even actually we tried other metrics as well. So we tried also to use, for example, a Kolmogorov distance. We tried to use also Hellinger distance, and that are more, let's say, frequently used by the stochastic distances, also the Mahalanobis and so on, right? But the Bhattacharya was the one that was working the best in very experiments we've done, and for one reason. For example, when you compare with the Hellinger distance, just use the square root, right? That means that practically distribution, the shape of the, if you look at the function, how the, so let me go to the components that should of this distance, right? Because both the Hellinger distance and the Bhattacharya distance are based on this factor. It is the factor that represents how much overlap there is between the PDF, right? The sum of the square root of this. And then what it changes is what kind of function you pass this factor to it, right? Now, with the Bhattacharya distance, the function is minus logarithm of the factor. That means that the distance, practically the Bhattacharya distance changes more. It's more, let's say, flat when there is almost a perfect overlap, and it's changing a lot when there is little overlap. By the Hellinger distance, it does the opposite. It changes a lot when you are very good, it changes a lot when there is just starts to get a bit of a difference in the overlap. But then it becomes very flat when there is almost no overlap. So because of this, practically, we couldn't really discriminate very well and evolve the set of parameters a lot when there is when the two distributions are far away. But and that's why we decided to use a Bhattacharya distance. But frankly, from testing multiple of them, we decided that this was actually the one giving us better performance and better evolution of into the parameter from the parameter space when changing this.
Yes, and I think it's, but please correct me if I'm wrong, I think it's crucial that your distances, the metrics that you're using here, that they're definitely symmetric, and it shouldn't make sense here, I think in this case, to have, for example, something like a Kullback-Leibler divergence here, which is not symmetric.
Yeah, exactly.
Yeah. Okay. Yes. And are there any problems when using, for example, when we're just looking here at this graph, if one of those PDFs that you're comparing here would be a very heavy tail distribution, would there be any problems?
Yeah, there might be that might create problems. So if we have heavy tails in the, so it means, but that of course would be also, remember, this is the distribution of the output of your model. That means that your model is creating data with a huge spread, right? And that means that also your or either the model or the experiment is having huge spread, right? So in both cases, I wouldn't really trust the model or the experiments.
Okay, then it's really you would suggest, okay, let's have a look at again at the experiment, or let's say refine your model.
Yeah.
Yes, and the second question, I think it's a nice thing to have this very simple density approximation that you used by using this staircase distribution. And did you investigate also some alternatives, like, for example, Gaussian mixtures? They're a little bit more complicated, have further parameters.
Yeah, we have tried that, and Gaussian didn't work so well. But I will tell you something. I know another group that solved this challenge problem, and they got also very good results. And they were actually not much different from us. They use also Bhattacharya distance and the hybrid uncertainties for the updating part, but for the model of the random variables, what they used was a beta mixture model. So practically, it's similar to Gaussian mixture, but when instead of mixing Gaussian kernels, you mix beta distribution that you can be on different spot and different position and so on. So they also got very good results. So of course, the mixture approach can also be good, but of course, they had much more parameters, right? So we already have a problem that we are increasing the input parameter space. That is already a problem that we are having, right? Because we are going from one epistemic uncertainty, from one epistemic variable, we're getting from one aleatory variable, we're getting 4 epistemic parameters for each of them. And then the problem with updating is that then the more the input space becomes big, the more difficult it becomes to solve, right? But they also got good results with beta mixture.
Okay, yes. I think that's a very interesting, let's say, insight. And yes, maybe my last and final question here would be, let's assume, for example, that we're using your approach in some, yes, let's say, dynamic kind of state estimation procedure, like a nonlinear generalization, for example, of a Kalman filter. There you would have not only this updating stage, the innovation stage, but also state prediction stage. And I think, at least my impression is, what would be easy to handle in your case when you have this staircase distribution is a numerical or numerical prediction step, just by performing the corresponding convolutions that you have to evaluate for the prediction step, just in a numerical manner, especially also for high-dimensional systems, just by performing a transformation into the Fourier space, and then instead of performing a convolution, perform just multiplications and transforming the result back. Yes. Is this also something you're investigating in some of your research?
This is something that I skipped a bit in this talk. I didn't explain well that practically when this can be seen in another challenge, right? So in the another challenge problem, the output was a time series, right? So what we did, I didn't explain that. We did, we used Bhattacharya, but I didn't really explain how. What we did practically, we were having a moving window comparing the output of the model, the dynamic output of the model, and dynamic data, and we were doing then a moving window approach and associating them and checking then the Bhattacharya distance of each window. And that was not very effective, not very efficient, and also not very precise. We didn't. So that what you said is very important. The treatment and the model reduction and how analyzing the data, it's very, very, very important to be to actually reduce then the dimensionality and having a better agreement between the model and the experiments. In fact, I would say that the best result I saw in this challenge problem were from a group that they did an analysis of the data and the output, and they used but they didn't use Fourier because Fourier was not working well here. Fourier we were having too many important frequencies, let's say, and they used the Prony method.
Okay.
They use Prony method. So, but then of course, then it's then of course it's a problem that you need to have practically a model reduction technique that is accurate and important and dedicating to the type of data you have, right? So of course, pre-processing the data is the right way to go, but that cannot be generic.
Yeah.
In this case, we tried to keep in our solution, we try to keep it as generic as possible. And in fact, as you can see, I mean, we use this method for this kind of observation for dynamics, as well as the method where the observation was just 2 points in the frequency space, right? And the algorithm was the algorithm we used was exactly the same, and it was just a difference how you define the likelihood. But of course, if you then have the pre-processing and you use this Prony method or Fourier or whatever transformation or reduction of the data, and it's of course that you lose in generality.
Okay, yeah. Thanks, Matteo. Do we have any other questions in the audience? Let me see, or is there someone who has written something in the chat? I think it doesn't seem to be the case that there's a further question. Final call for questions. Okay, if not, then again, many thanks, Matteo, for a very interesting presentation. And yes, as usual, we'll also put the slides on the webpage afterwards, if you send me them. Yes. And yes, then we can, yes, each of you can have a look at the inspiring presentation of the day. And the remaining thing is, I would like to wish you a nice Friday afternoon, evening, and weekend. And we'll see each other again on Friday in 2 weeks for the next seminar presentation that will be given by Radoslav Paulin from the Slovak Technical University in Bratislava.